Okay, welcome back everyone. So I should probably not be podcasting today because I don't have much of a voice. So I apologize for my strange sounding voice today. But we must move on. The show goes on. So the binomial probability distribution. We've been talking a lot about discrete probability distributions. So I like to think of it as general to specific. So the general case is discrete probability distributions. But we're going to zoom in and we're going to look at a special case of discrete, which is a binomial distribution. And then in the near future, we'll look at Poisson random variables. And then hypergeometric, I do want to note it's in the book, but we're not going to do that this semester. It's not in the curriculum, but you're welcome to read it. Okay, so determine whether our objectives for today, determine whether an experiment is a binomial experiment, compute the probabilities of certain experiments, compute the mean and standard deviation of a binomial random variable, and construct a probability histogram. Okay, so you have to have, this is big right here, you have to have your mental checklist. So in order for you to know whether you're running a binomial experiment, the experiment has to be performed a fixed number of tries, which is, I like to say, fixed n, fixed number of trials. Okay. All trials are independent. For each trial, there are two mutually exclusive outcomes, namely success or failure. So be on the lookout for probability of success, probability of failure. So I always tell people when you're reading a paragraph and you're trying to decide whether it's binomial, map out your N's, your P's, and your Q's. We're going to denote P for the probability of success and Q for the probability of failure. Okay, and the last item on the checklist there, number 4, is that the probability of success is fixed for each trial of the experiment. So note to self, probability of success is fixed. That means like flipping a coin, right? Each time you flip a coin, you still have a 50% chance of getting tails. So all trials are independent and the probability of success is fixed. Okay, let's just play with this. Are the following binomial experiments? A player rolls a pair of fair die 10 times. Right there you see your n trials. The number x of 7s rolled is recorded. Now I'm assuming insert the word sum there. Sum of 7. Because you're rolling a pair of die. So for example, if you roll a 1 and a 6, and that's going to give a sum of 7. If you roll a 5 and a 2, that's going to give a sum of 7. So you roll it 10 times and you basically record how many times you got a sum of 7. So if you think about it, is there a chance that you got a sum of 7 every single time? Sure, but it's small. So if you're counting the number of times you got a sum of 7, maybe you got it none, 1, 2, 3, all the way up to 10. And there would be a corresponding probability associated with each one of those events. And to compute those probabilities, we need to know more about the binomial, which we're going to know in a moment. But the answer to this one is yes. You have a fixed number of trials, you have a probability of success and a probability of failure. There's a probability for rolling a sum of 7, and there's a probability for not rolling a sum of 7. And all trials are independent. So this is a yes. This one, I have the answer written here, no. It's 11 largest airlines have on-time percentages of close to 85%. In order to assess reasons for delays, the FAA randomly selects flights until she finds 10 that were not on time. The number of flights X that needs to be selected is recorded. Well, the thing is, you don't know if she might have to select 20 flights, 30 flights, 80 flights, 1,000 flights until she finds 10 that were not on time. So the answer is no, it's not binomial because there's not fixed trials. There's not a fixed number of trials. Okay? I'll hit pause there as we continue our examples. Okay, in this next example, we want to actually start computing some things here. So suppose that a particular air carrier has an on-time percentage of 79%. I'll erase that so you can see it. On-time percentage is 79%. Suppose that 4 flights are randomly selected. So right away, I know my n is 4, my p is 0.79, my q is, if this is success, then failure is the opposite of that, which is 0.21. So you map that out, your n's, your p's, and your q's. It says construct a probability distribution for x, and clearly, we need to know this formula. So this formula is n choose x, p to the x, q to the n minus x, where I'm denoting q as 1 minus p. So if p is the probability of success, and q I'm denoting as the probability of failure. So if you can map these things out, it will be easy to plug and chug into that formula and create a distribution. So let's get started with that. We know it's going to be xp of x. And if you think about it logically, the number of on-time flights is recorded, so maybe none of them were on time, 1, 2, 3, or maybe all 4 of them were on time. Okay, so I'm going to just start to set up this formula here so you can just kind of see how I do it and catch a pattern. So clearly 4 is your number of trials. So 4 choose 0. Oh, this should say 4 over here. 4 is your number of trials. So 4 choose 0, 0.79 to the 0th, 0.21 to the 4th. That's going to give me my probability of having 0 flights on time. Then 4 choose 1, 0.79 to the 1, 0.21 to the 4, that's going to be p of 1. And so therefore I'll be able to compute these probabilities. Now, just to give you a little hint, anything choose 0 is 1, and anything to the 0th power in math is 1. So you really, with this first one, you just have to type out 0.21 to the 4th. So I'm going to record that. I'm going to type that out. 0.21 to the 4th is like 0.0019. So we know the answer to this is 0.0019. Okay? Now a lot of people say, what is this NCX button? You know that. That's your combination button. You know that, and I'll show you that on the calculator. Let's do P of 1 together. And unfortunately it made me take the writing away, but I want to show you how to type that out. So 4 choose 1, and then times 0.79 up caret 1, get that answer, and then times 0.21 up caret 3. So you start to notice how I'm using that formula. So we get 0.0293 about. So let me hit pause as we record that. Okay, so I do want to mention that, we clearly use the n choose x, p to the x, q to the n minus x. We used the binomial formula for computing these probabilities, but there is a button on the calculator which will make your life a little bit easier. So for example, if I wanted to verify this without using that formula, I could use the bin PDF feature of the calculator. So bin PDF n comma p comma x. So if I were to try and get this 0.029 using that feature of the calculator, n is the number of trials, that's 4. Probability of success is 0.79, and then x is the number of on-time flights that you're interested in, which is 1. So I just want to show you how to key that in to the calculator. So you would hit second distribution, go all the way down to bin PDF, and like I said, n is 4, probability of success is 0.79, and x is 1. You see, you got 0.029 either way. Alright? So just kind of showing you some features of the calculator there. And what's really cool, I want to show you another feature. Since we know that that's 0.029, if I hit second entry, I can trace back over it and now look at 2 flights being on time. See? And I can fill all that in. And I can go back and do it. Okay, now what about 3 flights being on time? Second entry, trace back over. Okay, now 3 flights being on time, it's 0.414. And then the last one, for all 4 flights being on time. See? So it's nice when you know how to do it on the calculator, basically, make your life easier, faster. 0.3895. Now the cool thing is, I'm going to pull up our probability distribution again. So like I said, in the end, you know you did it right because all of your probabilities should add up to 1. So when you're told to construct a probability distribution for x, you know that you did it right because all those probabilities should add up to 1. Okay, so let's scoot on down to the next problem. So we know now that this section you have to be very aware of words like at least, greater than, fewer than, because when you're living on a discrete distribution, when you're computing the probability that x happens, it depends what words are being used. You'll see that in a moment. So here, according to the automotive company, 35% of car-owning households have 3 or more cars. You survey 20 households. What's the probability exactly 5 have multiple cars? Exactly 5. So if I'm going to do this on the calculator, I'm going to do bin PDF n, p, x. So I'll do bin PDF, number of trials, which is 20, probability of success, which is 0.35, and the number, and then you're wanting exactly 5 households. So you can compute this, and I'll let you play with that. If you type that in the calculator, you're going to get 0.1272. So I'm leaning, now that I showed you the formula, and I'll just make one more brief mention of the formula. If you were going to use the formula, you'd have to do 20, the binomial formula, you do 20 choose 5, 0.35 to the 5, 0.65 to the 15th. But like I said, whether you crunch this out on your calculator or whether you use the bin PDF feature of your calculator, you should arrive at 12%. In fact, let's do that together. So second distribution, bin PDF, and then your trials is 20, your probability of success is 0.35, and then comma, you're choosing 5. See? 0.1271. It matches, or 0.1272 rounded. Okay, now let's try the next one together. Now, the trick is with this one, you don't see the word exactly, you see less than. So you still have the same sample size, n is 20, same probability of success, 0.35, but it says what's the probability that less than 4 households have multiple cars? All right, let me translate that. Less than. Probability that x is less than 4. Well, think about what less than 4 means. Less than 4 means 3 or 2 or 1 or none. So with this, option 1, I'm going to give you your options. Option 1 is to run, to basically do 20 choose 3, then 20 choose 2, then 20 choose 1, and then 20 choose none. Run that binomial formula for all 4 cases and add it all together. Or, better yet, use the bin CDF feature. Let's use the bin CDF feature of the calculator. So the thing is, though, when you use bin CDF, it's n, p, wherever your stopping point is. So less than 4, that's 0, 1, 2, or 3. So your stopping point's at 3. So that gets a little tricky. Here's the answer. Let me show you how we're going to get it. Second distribution, cumulative distribution function, CDF, because you're accumulating multiple events. So n is 20, P is 0.35, and your stopping point is 3. See? 0.044, which matches this answer. So notice this answer matches this answer. Okay? So again, when you're less than 4, so you're accumulating multiple events, hence the bin CDF feature, cumulative distribution function. So a lot of people say, okay, bin PDF is when I see the words exactly so many, and bin CDF is when I'm accumulating multiple events. Yes. All right, let's try the last one together. So it says in a random sample of 20 households, again, N is still 20, working on this one. What's the probability that at least 4 households have 3 or more cars? At least means greater than or equal to. Now this is where it gets tricky. At least 4 means 4 or 5 or 6 or 7, all the way on out till 20, because you had 20 households. So, or 8, all the way out to 20. But if I try to union those probabilities together, it's going to take forever. So instead, you use the complement rule, and I'm going to highlight that over here. Instead, you do 1 minus the probability of the opposite of what you're looking for. Use the complement rule. So what's the opposite of 4 or more? 3 or less. And it might help you to write that out. So instead, you're going to do 1 minus the probability of 3 or less, which would be 1 minus the bin CDF of n, p, 3. But the thing is, you had already done that in the step above. In part B. You had already done that. You had already done that in part B. So you end up taking 1 minus the thing that you got right here. So 1 minus 0.0444. Now, what I do want to mention is that, your options are slim. Option 1 is to run that binomial formula from 4 all the way on out till 20 and add those up. Or to do a separate bin PDF from 4 all the way to 20 and add that on up. But that'll take twice the amount of time as if you use the complement rule. So take 1 minus the probability of the opposite of what you're looking for. So the opposite, again, of 4 through 20 is 3 or less. And to get the probability of 3 or less, you would do bin CDF up to 3. Remember that the bin CDF feature is engineered to accumulate, on your calculator, to accumulate from 0 to 3. And that's why, that takes care of that for me, so I don't have to do a lot of by hand calculation. So then 1 minus 0.044 is your final answer, which would be about 0.9556. So this one, I didn't write it out there, but 0.9556. Okay, hope that helps. Let's see, that might be our last slide for today, or, I think there is one thing on the next slide. Yeah, and that won't be hard. Computing the mean and standard deviation of a binomial random variable. The big thing you need to know is that mu equals NP and standard deviation equals root NPQ, which you're seeing here. So let's just jump in. 35% of car-owning households have multiple cars, 3 or more cars, in a sample of 400. Determine the mean and standard deviation of the number of car-owning households that'll have 3 or more cars. So this is just practice using those formulas. So mu is our expected value, which is NP. So that's going to be, your sample size is 400. Your probability of success is 0.35. And like I said, my voice, sorry for the way my voice sounds, kind of losing it. So 400 times 0.35 is a 140. So your mean is 140. And your standard deviation, so that means you would expect 140 households out of those 400 to have, 3 or more cars. Standard deviation is root NPQ, so I'm going to let you key that in. So your N is 400, your P is 0.35, and your Q is the probability of failure, which is 0.65. You're going to square root that. So 400 times 0.35 times 0.65 is something, and then square root it, and you arrive at 9.5. So I'm just going to say down here that standard deviation is approximately 9.5 households. All right, that's it for the binomial random variables. I have other examples on podcast, on iTunes, of me doing problems from the book with you. Hope that helps. Good luck.